Welcome back to the deep dive, where we cut through the noise and get straight to the fascinating core of big topics. Today, we're embarking on a journey to our most captivating celestial neighbor, Mars.
That's right.
Forget everything you think you know about the red planet. We're going to peel back the layers of a cosmic mystery, exploring how this maybe once vibrant world transformed into the arid planet we see today, and what secrets it still holds for our future.
Uh-huh.
You don't need to be an astrophysicist to join this adventure. We're breaking it all down for you. Okay, let's unpack this.
Exactly. Our mission today is to give you a comprehensive yet, easily digestible understanding of Mars, especially tailored for those maybe curious about astronomy, but perhaps without a deep background.
Right.
We're distilling key facts from, a stack of sources, articles, research, our own notes, to give you those aha moments without the information overload.
Perfect.
From its fiery past to its potential future, we'll uncover what truly makes Mars tick.
So let's kick things off with the most iconic feature. Its color. You know it as the red planet, but have you ever wondered why it's red?
It seems obvious, but what's the actual reason?
It's not some grand mystery. Its surface is covered in incredibly fine iron oxide dust, essentially, rust.
Just plain old rust.
Pretty much. Just like rust on an old car, it gives Mars that distinctive orange-red hue. But look closer, and you'd actually see shades of golden, brown, tan, and even greenish, depending on the minerals present in the soil.
Ah, so not just red then. What's truly striking about Mars, especially when you compare it to Earth, is its fundamental differences. Imagine our planet, but shrinks significantly.
How much smaller are we talking?
Mars is roughly half the diameter of Earth, making its total surface area only slightly less than Earth's dry land area.
Okay, so still a lot of ground to cover, relatively speaking.
Yeah, but it also means you'd feel much lighter there.
Right.
Mars' surface gravity is only about 1/3 of ours, just double that of our own moon.
Wow, a third. That's a big difference.
And forget about breathing. It's a rocky, desert-like world with a very thin or tenuous atmosphere composed almost entirely of carbon dioxide.
Right, I've heard the air is super thin.
The air pressure on the surface is a mere few thousandths of what we experience here on Earth. This thin veil also means extreme temperature swings.
How extreme.
From a frigid -110 degrees Celsius, -166 degrees Celsius, up to a surprisingly warm 35 degrees Celsius, 95 degrees in equatorial summer.
Your T5C, that's like a nice summer day.
In certain spots at certain times, yeah. But that thin atmosphere just can't hold on to heat overall. It radiates away really fast.
Okay, this next part really got my attention. Mars isn't just a static red ball. It's a world with an incredibly dynamic, often violent past. You mentioned it formed billions of years ago. What was that tumultuous youth like, and how did it evolve?
Oh, definitely. That early history, from its fiery birth, truly shaped Mars. It formed about 4.5 billion years ago, growing rapidly like a giant cosmic snowball.
How did that work exactly?
As countless bits of rock and dust in the early solar system's swirling nursery, what scientists call the protoplanetary disk, collided and stuck together. Runaway accretion, they call it.
Gotcha.
One key takeaway from this formation is that Mars ended up with a higher concentration of elements with low boiling points, like chlorine and sulfur, compared to Earth.
Why is that?
Scientists think these might have been pushed outward by the powerful solar wind from our young, very active sun.
So Mars had this intense formation, but how did that play out over billions of years? What's its geological story?
If we look at the broader implications, Mars's geological history reads like an epic saga of transformation. We simplify it into three main chapters, or periods.
Okay.
The first is the Noachian period, from about 4.5 to 3.5 billion years ago. Imagine Mars's youth, a chaotic, maybe watery world, constantly bombarded by asteroids, forming valleys, eroding landscapes.
Sounds rough.
It was. But then, a pivotal event. It lost its protective global magnetic field, setting it on a path dramatically different from Earth's. That's sort of the core story of the Noachian period.
Losing the magnetic field, that's huge.
Absolutely critical. Next came the Hesperian period, roughly 3.5 to maybe 3.3, 2.9 billion years ago. This was an era dominated by widespread volcanic activity, unleashing immense floods that carved out huge channels we still see today.
Volcanoes and floods. Quite the combo.
Yeah, really reshaping the surface. Finally, we're in the Amazonian period, from about 3 billion years ago to the present. This is characterized by fewer impacts, continued, though maybe less intense, lava flows, and the formation of those enormous volcanoes.
Right. And when we look at Mars's surface now, it tells this dramatic story. There's that striking north-south divide, what scientists call the Martian dichotomy. The northern hemisphere is mostly flat, low-lying plains, while the south is this heavily cratered highland. What caused such a dramatic difference?
Well, the leading hypothesis for that vast difference is genuinely mind-blowing.
Lay it on me.
A Pluto-sized object might have slammed into Mars about 4 billion years ago.
Whoa, Pluto-sized.
Yeah. This catastrophic impact is thought to have created the enormous Borealis Basin, which is absolutely massive, about 10,600 by 8,500 kilometers.
That's hard to even picture.
It's roughly the combined area of Europe, Asia, and Australia. It truly is a testament to the planet's turbulent youth.
Incredible.
And the largest exposed crater, Hellas, is equally monumental, over 2,300 kilometers wide and 7 kilometers deep.
7 kilometers deep? That's staggering. But even today, Mars boasts some of the most impressive geological features in the solar system, right?
Absolutely. Take Olympus Mons, for instance. It's not just a mountain. It's the tallest volcano in the entire solar system.
How tall are we talking?
Soaring over 21 kilometers, that's 13 miles high from its base.
Okay, perspective.
That's about twice the height of Mauna Kea measured from the ocean floor, or roughly 3 times Mount Everest from the plains to its summit. It's so vast.
Yeah.
If you were standing on its base, you wouldn't even see the peak, because it's so far beyond the horizon, you'd essentially be climbing a mountain you couldn't see.
That's wild. And the canyons.
Then there's Valles Marineris, one of the largest canyons, stretching an astonishing 4,000 kilometers, 2,500 miles long, and up to 7 kilometers, 4.3 miles deep.
4,000 kilometers.
Its length is comparable to the entire continent of Europe, completely dwarfing Earth's Grand Canyon, which is, maybe 450 kilometers long.
Just puts it in perspective. And how did that form?
This immense canyon is thought to have formed from the swelling of the Tharsis area, a vast volcanic region nearby. Basically, the crust stretched and cracked open.
So under all these incredible surface features, what's Mars actually made of? Is it like Earth inside?
It is, in some ways. Just like Earth, it's differentiated into layers. A dense metallic core, a silicate mantle, and an outer crust.
And the crust.
The crust itself is quite thick, averaging 42 to 56 kilometers, which is actually thicker than Earth's average crust.
Is it still geologically active? Does it have quakes?
It does, and we know it's still active. NASA's InSight lander detected over 450 Marsquakes, confirming that the planet still trembles.
450, that's quite a few.
Yeah, and evidence even suggests a partially molten core, possibly with a solid inner core, a bit like Earth's. So things are still stirring down there.
But there's a crucial difference concerning its magnetic field that had a profound impact, isn't there? You mentioned it lost it.
Yes, that's one of the biggest distinctions. Mars lost its structured global magnetic field about 4 billion years ago, possibly due to numerous really large asteroid strikes.
And the consequence.
This means it no longer has the protective shield Earth does from the sun's harsh radiation, the solar wind.
So it's just getting blasted.
Pretty much. Yet, interestingly, parts of its crust are still magnetized, showing what we call paleomagnetism, like ancient magnetic ghosts trapped in the rocks.
What does that tell us?
It suggests that alternating polarity reversals, similar to those seen on Earth's ocean floors, might have occurred in the past. It even hints at the possibility of, maybe, past plate tectonic activity before its main magnetic field faded away. What's fascinating here is piecing together that ancient history.
So imagine standing on Mars right now. What would it feel like? Let's talk about that thin, dusty veil that is its atmosphere and what kind of weather you'd experience.
Okay, well, you'd immediately notice the atmospheric composition. It's about 96% carbon dioxide.
Almost pure CO2.
Yeah, with much smaller amounts of argon, nitrogen, and just traces of oxygen and water. It's also incredibly dusty, with tiny suspended iron oxide particles.
Rust dust.
Exactly, which, from the surface, give the sky a kind of tawny or even pinkish hue, not blue like ours.
Right, and the lack of magnetic field you mentioned, how does that affect the atmosphere directly?
As you mentioned, Mars lacks a global magnetic field. This means the solar wind directly interacts with this ionosphere. That's the upper layer of Mars's atmosphere where gas particles are charged, stripping away atoms and causing the atmospheric density to be very low.
So it's constantly losing its air to space.
Pretty much, yeah. Missions like AMEN are actively studying this atmospheric loss right now.
That sounds like a very quiet, eerie place. Does sound even travel well there.
That's a fantastic question. And the answer is not really. Due to the higher CO2 concentration and much lower surface pressure, sound actually gets muffled or attenuated much more. It dies out much faster on Mars.
So you couldn't shout very far.
Exactly. Researchers using the Perseverance rover have found that sound travels at about 240 to 250 meters per second, depending on frequency, which is significantly slower than on Earth. So things would sound quite different, probably much quieter, maybe a bit duller.
It's interesting how many parallels it has with Earth despite these differences. Mars has an axial tilt of about 25 degrees, very similar to Earth's 23.5 degrees.
Right.
So just like us, Mars experiences seasons.
It does, yeah. The catch is, because its orbital period is nearly twice as long as Earth's, its seasons last almost twice as long, too.
Makes sense. A longer year, longer seasons.
And due to its more elliptical or eccentric orbit, southern summers are more extreme. They experience temperatures up to 30 degrees Celsius, 54 degrees Arium, warmer than northern summers at the same point in the season.
So the orbit shape really matters for its climate.
Definitely. So while overall it's cold, these seasonal shifts are still quite pronounced and different between north and south.
And the weather isn't always calm, right? Dust storms.
Oh, you'd also contend with the largest dust storms in the solar system. These aren't just minor breezes. They can reach speeds over 160 kilometers per hour, 100 mile per hour,
Oh.
and sometimes even engulf the entire planet, increasing global temperatures significantly because the dust absorbs sunlight.
A planet-wide dust storm. Hard to imagine.
And unlike Earth, Martian auroras, as detected by the UAE HOPE orbiter, can encompass the entire planet
Why is that?
because of the lack of a global magnetic field to funnel those charged particles from the sun towards the poles. They just kind of interact everywhere.
So auroras everywhere.
Potentially. We even saw a massive solar storm in 2017 temporarily double radiation levels on the surface and cause auroras 25 times brighter than previously observed. So not only is it cold and thin, but you also have to worry about a planet-sized dust allergy and a potentially global cosmic light show.
So what does this all mean for the big question? Water on Mars. It's something that's fascinated us for ages, and the evidence seems, well, truly compelling.
Indeed. Currently, most of Mars's water is locked up as ice. It's in the form of dust-covered ice at its polar caps.
How much are we talking?
The south polar ice cap alone holds enough water to cover most of the planet to a depth of 11 meters if it were to melt.
11 meters deep, planet-wide? That's a lot of water.
It really is. We also see water ice filling large craters, like Korolev crater, which contains approximately 2,200 cubic kilometers of ice. That's like a huge frozen lake just sitting there.
Okay, so plenty of ice. But liquid water? Can it exist on the surface now?
Not really. Liquid water, as we know it, cannot persist on the surface for extended periods because Mars's atmospheric pressure is so incredibly low, less than 1% of Earth's.
Right, you mentioned that. So what happens to it?
Any liquid water would quickly sublimate, turning directly into gas like dry ice does on Earth. It just boils away into vapor almost instantly.
But that doesn't mean it wasn't there in the past, right? That's the real mystery, the evidence for ancient oceans or lakes.
Exactly. This raises an important question. What about the evidence for past liquid water? And there's a lot of it. We see huge linear swaths of scoured ground called outflow channels.
Like giant riverbeds.
Bigger than riverbeds.
Think
Catastrophic flood paths, like Madame Vallis, which is 700 kilometers long, much greater than the Grand Canyon. These suggest massive sudden releases of water, maybe from underground aquifers bursting.
wow. What else?
Then there are finer dendritic valley networks and gullies in older regions, which look much more like runoff from past precipitation, rain or snowmelt or possibly melting ground ice.
And actual lake features.
Geological features like deltas and alluvial fans found inside craters also point to past warmer, wetter conditions and widespread crater lakes. They look just like features formed by water here on Earth.
And the mineral evidence really makes a strong case, doesn't it?
It absolutely does. Discoveries like the minerals jarosite and gypsum, found by the Opportunity rover, along with hematite spherules, blueberries, and goethite. These minerals typically form in the presence of liquid water.
So the rocks themselves are telling us water was there.
Precisely. More recently, Curiosity rover data showed significant mineral hydration, meaning water molecules bound within the minerals, with up to 4% water content by weight in subsurface soil samples.
4% water in the dirt.
Yeah. And perhaps most astonishingly, in 2016, NASA reported finding a massive amount of underground ice in a region called Utopia Planitia,
How much ice?
estimated to be equivalent to the volume of water in Lake Superior. Just buried under the surface.
Lake Superior underground on Mars.
And even more recently, the ExoMars Trace Gas Orbiter spotted indications of subsurface water ice, potentially large amounts, in the Valles Marineris Canyon system itself.
This all ties into the intriguing ancient ocean debate, where some scientists theorize that much of the low northern plains were once covered by an ocean.
Possibly the size of Earth's Arctic Ocean, yeah.
How do they support that idea?
That theory is certainly supported by looking at the ratio of deuterium, that's a heavier type of hydrogen atom, to regular hydrogen, protonium, in the water vapor in the Martian atmosphere.
What does that ratio tell us?
It's much higher on Mars than on Earth. This suggests that Mars has lost a tremendous amount of its lighter water over billions of years, likely stripped away into space, leaving behind a higher concentration of the heavier variety.
So the water loss points to a wetter past.
It does. However, it's a complex picture. Martian climate models haven't yet definitively shown the planet was warm enough for long enough to support such large, persistent bodies of liquid water globally. It's still an active area of research.
And what about those weird dark streaks people were excited about, RSLs?
Ah, yes, the recurring slope lineae, or RSL. These are dark streaks that appear, grow, and fade on certain slopes during the Martian summer. Initially, they were considered really strong evidence for flowing liquid brine, salty water that could stay liquid at lower temperatures. But later research, analyzing them more closely, suggested they might actually be dry, granular flows, like cascades of sand or dust, perhaps triggered by very small amounts of water ice melting, but not necessarily flowing liquid water itself. So the definitive conclusion remains elusive, showing how dynamic and complex Mars continues to be. We're still figuring it out.
Let's zoom out a bit and look at Mars's celestial dance with the sun and its own unique companions. Where does it sit in the solar system?
Okay. Mars is the fourth planet from the Sun, orbiting at an average distance of about 230 million kilometers, 143 million miles. A Martian year, the time it takes to go around the Sun once, is 687 Earth days.
So almost 2 Earth years.
About 1.88 Earth years, yeah. But a Martian solar day, or sol, is only slightly longer than an Earth day, at 24 hours, 39 minutes, and about 35 seconds.
That's remarkably close to our day length.
It is, which is convenient for operating rovers. Its axial tilt at 25.19 degrees is also quite similar to Earth's 23.5 degrees, which is why it experiences seasons, as we discussed, though they are nearly twice as long.
And its orbit isn't perfectly circular.
Right. Mars also has a more elliptical or eccentric orbit compared to Earth. Its eccentricity is about 0.09. This means its distance from the Sun varies more significantly throughout its year, impacting its climate and also how bright it appears to us in our night sky.
And it has a couple of very peculiar moons, Phobos and Deimos. They're not round like our moon.
No, not at all. These are two small, irregularly shaped natural satellites looking more like captured asteroids. Phobos, the larger of the two at about 22 kilometers in diameter, orbits incredibly close to Mars.
How close?
So close, in fact, that from the Martian surface it would appear to rise in the west, zip across the sky, set in the east, and rise again in just 11 hours, much faster than Mars itself rotates.
That would look so strange, rising in the west.
Yeah, and this orbit is gradually lowering due to tidal forces. Scientists predict in about 50 million years, it could either crash into Mars or be torn apart by Mars's gravity and form a ring system.
Wow, a future ringed Mars. And Deimos.
Deimos, the smaller one at about 12 kilometers in diameter, orbits further out and rises much more slowly in the east, taking longer to cross the sky.
Where did these little moons come from? Are they captured asteroids?
That's the big debate. They're low albedo, meaning they're quite dark and don't reflect much light. And their composition resemble C-type asteroids, which supports the capture theory.
What?
But their orbits are very nearly circular and lie almost exactly in Mars's equatorial plane. That's unusual for captured objects, which you expect to have more tilted eccentric orbits.
So what's the alternative?
Another theory suggests they might be fragments of an older, larger Martian moon that got destroyed, or perhaps debris from a large impact on Mars itself that reaccreted in orbit. We don't know for sure yet.
It's amazing to think that these tiny moons have played such a role in understanding the planet's past. Our fascination with Mars goes way, way back, long before telescopes or rovers.
Absolutely. Mars has always been noticeable, this distinctly red wandering star in the night sky. Ancient Sumerians named it Nergal, their god of war and plague.
The war god connection seems common.
It does. The Greeks called it Ares, their god of war. And the Romans, of course, named it Mars for their god of war, associations that have stuck with us.
Did ancient cultures just see it or did they track it?
Oh, they tracked it meticulously.
Yeah.
Ancient Egyptians and Babylonians recorded its movements very accurately, including its curious retrograde motion, where it appears to move backwards against the background stars for a time.
Right, that puzzled people for ages.
It did. And in the 4th century BCE, the philosopher Aristotle even noted Mars disappearing behind the moon during an occultation, which helped him argue that Mars must be farther away than the moon, a key astronomical observation.
And then in the early modern era, things really started to take shape scientifically.
Big time. Johannes Kepler, using Tycho Brahe's incredibly precise pre-telescopic observations of Mars, famously deduced Mars's elliptical orbit around the Sun in 1609. That was a monumental shift from the ancient idea of perfect circular orbits.
A cornerstone of modern astronomy.
Absolutely. Just a year later, Galileo Galilei was among the first to observe Mars with a telescope, though his early instruments couldn't resolve much detail. But the 19th century brought us one of the most enduring and, well, captivating myths about Mars. The Martian canals.
Ah, yes, the canali. Tell us about that.
It started with the Italian astronomer Giovanni Schiaparelli. In 1877, observing Mars during a favorable opposition, he noted networks of fine linear features on the surface, which he called canali.
Which just means channels in Italian, right?
Exactly. Channels or grooves, natural features. But the term was mistakenly translated into English as canals, implying artificial construction.
And someone ran with that idea.
Oh, yes. Percival Lowell, a wealthy American astronomer, became obsessed with the canals. He built his own observatory in Arizona, largely to study Mars, and produced intricate maps showing hundreds of canals, arguing they were vast irrigation systems built by an intelligent Martian civilization to channel water from the poles to their dying, drying equatorial regions.
That's quite a narrative.
It completely captured the public imagination, fueling decades of science fiction about Martians. However, with larger and more powerful telescopes in the early 20th century, other astronomers couldn't confirm Lowell's canals. They were eventually understood to be optical illusions, perhaps created by the brain connecting faint, unrelated dark spots seen near the limit of resolution, combined with wishful thinking.
So no canals, but the myth, in a way, sparked real exploration, didn't it?
It certainly fueled the desire. The mid-20th century marked the dawn of robotic exploration, utterly revolutionizing our understanding. After a string of early Soviet and U.S. failures,
Hard.
very hard, especially back then. But Mariner 4 in 1965 made the first successful flyby, sending back just 22 grainy close-up images of a cratered surface. It was the first glimpse of another planet up close, and it definitively showed no canals, revealing a moon-like barren landscape. Bit disappointing at the time, perhaps.
But groundbreaking.
Absolutely. Then Mariner 9 in 1971 became the first spacecraft to successfully orbit another planet. It arrived during a global dust storm, but once the dust cleared, it mapped huge volcanoes, valles marineris, and features suggesting past water flow. It revealed the real, complex Mars.
And the landers.
The Viking probes in the mid-1970s were the first successful landers. Viking 1 and 2 touched down, took panoramic photos, analyzed soil, and conducted biological experiments designed to detect life.
Did they find anything?
The results were ambiguous and are still debated by some scientists today. Some tests seemed positive initially, but other instruments found no organic molecules you'd expect life to leave behind. The consensus became that the results were likely due to unusual soil chemistry, not life, but it was our first real search for life on the surface.
And since then, the exploration hasn't stopped.
Not at all. Since 1997, with Mars Pathfinder and its little Sojourner rover, we've had a continuous robotic presence at Mars. Multiple orbiters like the 2001 Mars Odyssey, Mars Express, the incredible Mars Reconnaissance Orbiter, MAVE studying the atmosphere, the UAE's HOPE Orbiter, China's Tianwen-1,
And the rovers?
and the amazing rovers on the ground. Spirit and Opportunity, the car-sized Curiosity Lab, and now Perseverance with its helicopter Ingenuity. They're all operating simultaneously or have operated recently, providing an unprecedented stream of data. NASA even has interactive tools like Mars Trek and Experience Curiosity Online, letting anyone explore this data.
What's next? What are we looking forward to?
The pace is only accelerating. Looking to the future, NASA's ESCAPADE mission to study the magnetosphere is planned for 2025. ESA's Rosalind Franklin rover, designed to drill deep for signs of life, aims to launch no earlier than 2028 after delays. There's a joint NASA-ESA concept for Mars sample return, starting perhaps later this decade.
Bringing rocks back to Earth.
Exactly.
Yep.
China also planned its own sample return mission,
Wow.
Tianwen-3, around 2030. And then you have private companies like SpaceX, with very ambitious plans for human colonization, maybe even within 20 years, using their Starship system.
It's incredible, though all these missions must leave some stuff behind.
Ah, yes. It's estimated there's over 7,000 kilograms, or about 7 tons, of human-made debris scattered across the Martian surface, from landed missions, crash sites, and discarded hardware. A bit of interplanetary littering.
Okay, that brings us to the two most captivating questions. Is there life on Mars, or was there ever? And can we, as humans, actually live there ourselves someday?
Right, the ultimate questions. The search for life has this long and often dramatic history. As we said, late 19th century astronomers widely believed Mars supported life, maybe even intelligent life.
Lowell's canals.
Exactly. But early spectroscopic studies by astronomers like W. W. Campbell eventually disproved the presence of significant oxygen and water vapor in the amounts needed for Earth-like life, effectively dampening that enthusiasm early on. The Viking experiments in the 1970s, as we mentioned, gave those initially positive but ultimately disputed results regarding microorganisms in the soil. Today, we know the current Martian environment is incredibly harsh for life as we know it.
How so? Remind us.
Very little heat transfer across the surface, poor insulation against damaging solar and cosmic radiation due to the lack of a global magnetosphere and thin atmosphere, and insufficient atmospheric pressure for liquid water to be stable on the surface. Plus,
There's more.
Martian soil contains toxic perchlorates. These are salt-like chemicals that are highly oxidizing. They're great for potential rocket fuel, maybe, but really bad for organic molecules. They'd likely destroy any money on the immediate surface.
Okay, so it sounds pretty dire for surface life now, but are there any intriguing clues that keep scientists hopeful about past life or maybe life hiding underground?
There are still some tantalizing clues. The detection of methane in the atmosphere, for example, is puzzling,
Why methane?
because methane breaks down relatively quickly in the Martian atmosphere due to sunlight. So if it's there consistently, even in tiny variable amounts, it suggests an active source replenishing it. That source could be geological, like water rock reactions underground, or potentially biological, produced by microbes.
So, geology or biology, we don't know which.
Not yet. Formaldehyde has also been detected, which also has a short lifetime. Finding impact glass is another interesting thread.
Impact glass.
Yeah, created during meteorite impacts. On Earth, impact glass is known to sometimes preserve biosignatures, evidence of past life, remarkably well. And we found deposits of it on Mars.
Places to look then.
Definitely. And just recently, in June 2024, the Perseverance rover analyzed a rock nicknamed Cheava Falls, which NASA designated a potential biosignature. It was features that could be consistent with biological processes, but natural geological explanations are also possible. So its origin isn't yet definitively biological. The search continues, ever hopeful, digging deeper.
And as for us living there, what are the human health risks, especially from radiation? That seems like the real silent killer, doesn't it?
It truly is the biggest, most insidious challenge for long-term human presence on Mars. It's a fundamental problem. Unlike Earth, Mars has no global magnetic field shield and a very thin atmosphere, offering minimal protection from deep space radiation.
What kind of radiation are we talking about specifically?
We're talking about two main types that are concerning. First, galactic cosmic rays, or GCRs. These are high-energy particles, atomic nuclei stripped of their electrons, accelerated by supernovae and other events outside our solar system. They're constantly bombarding us, and they penetrate deeply into materials, including spacecraft and human tissue, creating a complex, mixed radiation field of secondary particles.
Sounds nasty. What's the other type?
The other is solar particle events, or SPEs. These are bursts of energetic particles, mostly protons, ejected from the sun during solar flares or coronal mass ejections. While Mars's thin atmosphere can shield the surface from the direct, lower-energy SPE particles, the more energetic ones can still get through, and both types can create secondary neutrons when they hit the atmosphere or ground, and those neutrons are also harmful.
So how much radiation are we talking about compared to, say, the space station?
During the transit cruise phase to Mars, radiation levels are estimated to be about 2 to 3 times higher than what astronauts experience on the International Space Station, ISS, in low Earth orbit, which still benefits from some of Earth's magnetic shielding.
And once you land on Mars?
On the Martian surface, the average daily dose is actually somewhat similar to that on the ISS, around 0.64 millisieverts per day. That's because you get shielding from the planet itself, blocking half the sky, and some from that thin atmosphere.
It's a catch.
Yes, Large solar particle events, those solar storms, can cause dramatic radiation spikes on the surface, delivering a large dose in a short period, which is a major acute concern for astronauts caught outside a heavily shielded habitat.
And what are the actual long-term health consequences for astronauts from this constant exposure?
Exposure to this chronic GCR radiation and potential acute SBE doses carries significant health risks. It's not just an increased lifetime risk of cancer, carcinogenesis, which is a major concern. It can also cause both acute and late central nervous system effects.
Affecting the brain.
Yes, impacting cognition, memory, motor function, potentially behavior,
Right.
and increasing the risk of neurological diseases later in life. There are also degenerative tissue effects, like cardiovascular disease, cataracts, and immune system dysfunction. We just don't fully understand the long-term impact of GCRs on the human body yet.
So what are we doing about it? How can we possibly protect astronauts?
That's the multi-billion-dollar question. Scientists are actively researching mitigation solutions. This includes developing effective shielding for habitats and transit vehicles. We're taking maybe 10 to 20 centimeters of water-equivalent material, which is heavy and expensive to launch. Water, polyethylene, even Martian regolith itself could be used.
What else besides shielding?
Improving space weather forecasting is critical to predict SBEs so astronauts can take shelter. Continuously monitoring crew health and radiation exposure is essential. And researchers are developing potential biological countermeasures, drugs, or therapies that could help protect cells from radiation damage or enhance repair mechanisms. But much more research is still needed before we can confidently say we can keep humans safe on long-duration Mars missions.
Despite these immense challenges, human mission proposals continue to proliferate. It seems like the drive to go is still strong.
Incredibly strong. Well, a recent NASA internal study reportedly found crewed missions in the early 2030s technically unfeasible under current budgets and timelines.
Others are pushing ahead.
Yes. China has publicly stated plans for initial crewed missions, possibly around 2033. And private companies like SpaceX, led by Elon Musk, have the explicit goal of establishing a permanent, self-sustaining settlement on Mars, aiming for launches within the next decade or two, utilizing their reusable Starship system and ideas like in situ resource utilization living off the land.
Using Martian resources.
Exactly. Making water, oxygen, even rocket fuel from Martian ice and atmosphere. There are even concepts like using Phobos, the inner moon, as an anchor point for a future space elevator to make getting to and from the surface easier. The ambition is huge.
That kind of ambition for human settlement really makes you think about our future, doesn't it?
It really does.
Yeah.
If we connect this to the bigger picture, Mars is a primary target for human exploration, not just for its scientific value understanding planetary evolution, searching for life, but because it represents that next frontier for humanity, a potential second home.
A backup plan, or just expansion.
Maybe both. As we continue to peel back the layers of the red planet, uncovering everything from, vast hidden ice deposits that hint at past oceans to the complex dance of cosmic radiation that challenges our very presence there, it makes you reflect on just how much more there is to learn.
Absolutely.
And perhaps the most profound discovery won't just be about Mars itself, but about what its exploration reveals about our own place in the universe, our own planet's fragility and resilience, and ultimately what we're capable of, the challenges we can overcome as a species when we set our minds to it.
A truly thought-provoking way to wrap up our depth dive into Mars. It's been an incredible journey, from those ancient observations of a red dot through the canal myths to the cutting-edge science of today, transforming our understanding from, that mythical world to this complex, geologically active planet with a challenging but potentially rich history.
It really underscores how much we've learned, but also how much more is waiting.
Exactly. Thank you for joining us on this exploration, and we hope you walk away with a newfound appreciation for our enigmatic and maybe not so distant neighbor.